Good morning, Dr. Ahmad Zamani, our special speaker today, who has already joined with us. And good morning, everybody. So this morning, we will hear from Dr. Ahmad Zamani, a special topic about zeolite. So without further ado, I will give that full time to Pak Rainer, mungkin Prof. Rainer to start
Yeah.
this seminar this morning.
Right. Thank you, Bisinche.
Yes,
Good
please.
morning for everybody, especially for our guest speaker, Dr. Zamani from UMPSA. Thank you for your kind of delivering your expertise, especially in doing chemistry catalyst, chemistry of making gases. It's very insightful for us so that for information, our MRT is monthly. We do every month, and we invite speakers from uh, our college from Indonesia and as well from Australia and also from Malaysia, as we have MOU between UMPSA and our university. So it seems that this MRT is an initial task of doing or of implementing our MOU, and we hope we can do maybe another programs between UMPSA, between Dr. Zamani. We have we had Dr. Fasihi last years. We had Dr. Fasihi talking about computational chemistry, and he also asked for doing maybe global classroom. So maybe next we could discuss any kinds of programs that we can run together between UMPSA and Undana as well, especially for our Department of Chemistry here in Undana. Thank you, Dr. Zamani, for your time and your kind for sharing to us, for our students, especially for our students and our colleagues here in our school or department, and hopefully we can get something, or maybe uh, we can maybe join research. Maybe we have 2 or 3 colleagues here that they are uh, need to continue their study. Maybe they can join Dr. Zamani's group there in UMPSA for their PhD degree level, so that maybe this talk could incite them all, and hopefully we can enjoy this MRT. Thank you for us to participate in this occasion. Thank you, Ibu Sinche. Then I open this talk with bless of God. Hopefully, this talk will be beneficial for us. Thank you very much.
Thank you very much, Prof. Rainer. And next, we already know that this morning we will hear from Dr. Zamani. So, Dr. Zamani, the time is yours. We have like 1 hour to hear from you.
Okay, right. Okay, firstly, I would like to thank you, okay, to Prof. Rainer.
Rainer, yes.
Yeah, and then also for community of Materi Research Talk at University of Nusa Cendana for this opportunity to share my research. Okay, so I share my slide. This one. Okay, do you see my slide?
Yeah, it's clear here.
All right, clear. Is full screen? No. Okay. Right. Okay. Okay. So Assalamualaikum warahmatullahi wabarakatuh, and good morning, everyone. Okay, so yeah, okay. So today I would like to share my research works about choline derived isolate sodium A supported nickel-based catalyst CO2 conversion to renewable methane. Okay, so I introduce a little bit myself. I Dr. Ahmad Zamani from University Malaysia Pahang As-Sultan Abdullah-UMPSA under faculties Industrial Science and Technologies. Okay, so this little bit we go to the first slide about introduction and problems. Okay, so as we know, every year CO2 emission increase. Okay, so the increase of CO2 emission to atmosphere is huge concern which contribute to global warming. Okay, so CO2 is one of GSG, or we call as green house effects. Okay. Okay, so how to all right. So what affects CO2? CO2 attract the heat. Okay, the attract the heat and leading to a rise in Earth's temperature with global warming. Okay, so our world we hot. Okay, so we need to tackle this issue. Okay, so the best I think one of the technology how to reduce or to reduce CO2 emission, we can use technology we call as power to S. Okay, power to S. It means we use renewable energies. Renewable energy can be you can use solar or wind turbine. Okay, and also use green hydrogens. Okay, it means produce hydrogen from waters. Okay, using electrolysis and powered by renewable energies. Okay, and then this green hydrogen we combine with CO2 to produce S. It means as it can be produced methanol, methanes, or others hydrocarbons. Okay, so why we need to this technology to achieve? We have a policy here, policy to we call as net zero 2050. Okay, so we need to net zero carbon dioxide emission. Okay, next slide. Okay, so we more focus on we call as power to renewable methane. Okay, so in this sorry. Okay, so in this power of methane combined with a few unit. Okay, here CO2 source can be we can get from gas field or from offshore. Okay, from offshore, or we can get CO2 from industries also, and the last one also from biogas. Okay, biogas. So the first unit we need to we call as CO2 capture. Okay, so we need to capture this CO2, and then we store to CO2 tank. Okay, the second unit in this technology we call is renewable energies. Okay, so renewable energy we can get from solar or wind turbine. Okay, wind turbine to generate electricity, and also the excess electricity we can supply to the reactors and others. Okay, and the third unit in this system produce green hydrogen. Okay, we produce green hydrogens from waters, just using waters, using technology electrolysis, and provide by renewable energies. Okay, and the last one unit is we call as renewable methane and storage reactors. Okay, so this is we call as CO2 methanation reactors. Is we combine with CO2 with hydrogens, and can convert to methane. Okay, and can convert to methane and waters, and then we store methane in the tank. So a few application we can use for methane. The first one, okay, we can inject to natural gas pipeline. Okay, natural gas. Okay, so we inject to natural gas pipeline. So also it can be used for fuel of vesicles, and also for starting material for to produce value-added chemicals and other fuels. Okay, so this is a main concept of power to reverse methane. Okay, so we focus more focus on CO2 methanation. Okay, CO2 methanation, because in this system, okay, they have two they have two limited because the technology, this technology is still high cost. Okay, they have two main issue. First one is the costing of produce green hydrogen. Okay, so for produce green hydrogens, they high cost, and then also for CO2 methanation, they use catalyst work at high temperature. So when we work high temperatures, we require reactor can stand high temperature, and we need a lot of cost. Okay, so we focus more on CO2 methanation reactor. Okay, this is a CO2 methanation reactor, is to convert CO2 with hydrogens to renewable methane. Okay, through catalytic process. Okay, so we require catalyst to convert CO2 to methane. Okay, so this part of the system. Okay, so this the equation require CO2. We need 4 more hydrogens, and then through the catalyst, and then we can get methane and waters. Okay, so the current catalyst, okay, normally they use nickel catalyst. Okay, nickel catalyst, but nickel catalyst high activation energies. This means we need a high temperature reaction. So more than 350 degrees Celsius. Okay. So also nickel operate at high pressures, 10 to 30 bar, and also poor thermal stability and deactivation due to the sintering and carbon formation. Okay, sintering and carbon formation due to the operation work at high temperature. Okay, so you can see here this energy diagrams. Okay, activation energy for CO2 methanation. Okay, so you can see catalyst, nickel catalyst require high activation. They have high activation energy. So we need to innovative catalyst. We need to develop new catalysts which can work at lower activation energy. Okay, so this is a lower activation energies. Okay, so why a low CO2 conversion below or low temperature? Because nickel hydrogen deoxidation is not active or low H2 dissociation, and also low CO2 absorption and activation. And the last one is a surface reaction to form methane. Okay, so these three factors why low CO2 conversion. Okay. Okay. So here strategies to enhance the catalyst activity at low temperature. So we they have three focus. Here is first one is improve hydrogen deoxidation. So we chose method chose and diffusion. Okay, so we use highly diffusion nickel nanoparticles. It means we produce smaller nickel particle around nano size. Okay, to expose more active site, and then can improve hydrogen splitting at lower temperatures. And second one is you can add a non-bimetal, but non-bimetal is very expensive. Okay, like a ruthenium IH or platinum. Okay, but there has a superior hydrogen activation because this method can spray over hydrogen onto nickels or the support and increase our activities. Okay. Number two strategies is to enhance CO2 absorption. Okay, enhance CO2 absorption. Use Syrian oxide as promoters. Okay, we use Syrian oxide as promoters because this series there has oxygen vacancies. Okay, that's interest with CO2 and lowering the energy barrier for activation. Okay, and number three, both methods support interaction. Okay, so a strong interaction nickel and the zeolite sodium A help to stabilize a small nickel cluster. The second one can modulate their electronic properties and promote charge transfers with reduced activation energy for both hydrogen and CO2 reaction. Okay, next slide about we use choline, okay, choline to produce zeolite sodium, okay, because natural choline as raw material, low cost, also abundant. We can get in Malaysia, 18 in Indonesia, similar. It has abundance and environmentally friendly source. Okay, so kaolin is alumina silicate OH. Okay, so it's layered by alumina silicate clay minerals. Okay, so we use alkali hydrothermal synthesis. Okay, kaolin can be converted to zeolite sodium A, LTA structures with ratio silica alumina ratio and high ion exchange capacities, and also uniform microporosity. Okay, so this zeolite picture for zeolite structure. Okay, and zeolite sodium A as a catalyst support, because zeolite A they have a uniform pore size, okay, around 4 angstroms, and also ideal for smaller molecule diffusion. Okay, they're good for CO2 and hydrogens. Okay, and then number 2, why we use zeolite sodium A, because high surface areas and IOH sites that allow nickels to plus loadings. And then the last one is because of thermal and mechanical stability in critical high temperatures methanation. Okay, it can work to 250 until 400 degrees Celsius. Okay, and also zeolite basic size can interact with CO2, acidic CO2, and this can enhance the absorption and activation. Okay, so this that's why we use zeolite, and also we use from kaolin. Number 3, use nickels as active site from methanation. So for nickel, we produce a small size around nanometers. Okay, so as we know, nickels active metal for CO2 methanation. Okay, so this is a equation for CO2 methanation, and nickel can facilitate CO2 activation, and also for hydrogen deassociation and CO bond cleavage. Okay, so nickel diffusion, particle size and metal support interaction strongly influence activity and cell activity. Okay, and the last one, we use surveillance or serum outside as promoters, because severe they have oxygen storage capacity. Okay, and then this storage can facilitate CO2 activation and improves resistance to carbon deposition. Okay, next we go to the methodology, how to produce sodium zeolite sodium A from choline. So this is a step here. So we need to firstly we need to pre-treatment, and then it has we need put in alkali hydrothermal. Okay, and then filter, and then crystallization, and the last one is we need to calcine at 550 degrees Celsius. Okay, and then after we get zeolite sodium A, we use method wet impregnation methods to coating or loading nickels and Syrian catalyst methods. Okay, so we follow this procedures method. Okay, so this for catalyst preparation. Okay, next after we finish or successfully synthesize catalyst, we need to evaluation of the catalyst using CO2 methanation unit, or we also call as feedback reactors. Okay, so this diagram, okay, so it has 10 for hydrogens, nitrogens, and also CO2. Okay, so mix this gas and go to the reactors furnace. Okay, so here we put catalyst in the glass tubes or quart tubes. Okay, and then and the product we detect with gas TCDs. Okay, gas chromatography DCD detectors. Okay, so this is actual for reactors. Okay, okay, so we go to the result, a few result. The first one is about SRD result. Okay, so this SRD result for A is choline. Okay, raw material choline, and then B is synthesized solid sodium A, and C is commercial solid sodium A. Okay, so you can see from SRD, you can conclude that we successfully synthesize solid sodium A from choline compared to the SRD commercial sodium A. Okay, so the structure is similar for B and C. Okay, and then the next
adalah tanaman industri pertanian.
The next is a send image. Okay, send image for synthesized solid sodium A from choline. So you can see here the image is like qubits. Okay, qubits. So this solid sodium A morphology image. And then BET result. Why they have? Okay, BET result. So we analyze using surface areas, BET surface areas, 3 sample, synthesis solid A, and then nickels with solid sodium A, and then nickels series solid sodium A. Okay, so you can see here, synthesized solid A, they have high surface areas around 217.1. Okay, and then when we add nickel to zeolite, the surface areas is reduced to 180.3. Okay, and then when we add one more metal series, the BT surface areas increase, okay, to 201.8. Okay, okay, so next go to the performance or CO2 methanation. Okay, we test the catalyst in feedback gas reactors. Okay, so you can see from this table, a nickel catalyst without zeolite sodium support, they can convert CO2 conversion 43.1% and selectivity 90% for methane. Okay, and then when we test with nickel zeolite sodium A with zeolite as a support, the CO2 conversion increase to 61.7% and also improves the selectivity to 100%. Okay, and when we put add co-promoters surveillance, CO2 conversion increased to 83.5%, and also they have similar selectivity with nickel zeolite 100%. Okay, so we can conclude that when we combine with nickels and ceriums with zeolite sodium A, they can improve CO2 conversion, also can improve methane selectivities. Okay, and also this catalyst can work at a median temperature 300 degrees C compared to nickel's catalyst, they work at 350 degrees C. Okay, so this is our methanation strategy or roadmap for implementation of renewable energies, renewable methane. Okay, so carbon is our current stage. We produce or synthesis catalyst small scale production. Okay, so also we test in small feedback reactors. Okay, so the next plan, we want to test our catalyst in pilot scale, also to produce or synthesis catalyst at pilot scale to scale out our catalyst. And then the next stage, we hopefully can apply this catalyst to industrial scale. Okay. Okay, so this work to support net zero emission 2050, and also to support SDG goal, SDG goal 30, climate action. Okay, and then also goal number 7, to ensure access the affordable, reliable, and sustained and modern energy for all. Also, this research support to CO2 test. Okay, so in Malaysia, we now we have more we more to CO2 test. Okay, as been that's all my presentation, or I share my sharing about my research works. So this pilot plant for CO2 methanation. Okay, the left side. Okay, is CO2 methanation at pilot scale, and also I also work in a pilot plant for power to reimburse methanes. Okay, this pilots combined with green hydrogens, and also they use renewables energy, solar, and also they have a methanation unit, and the last one is a storage for methane. So this is combined 4 unit. Okay, I think that's all. My presentation.
Okay, thank you very much, Dr. Zamani, for sharing your research finding and knowledge. And I believe that all of us here learn so much from what you've shared with us this morning. So here, Dr. Zamani, we have our colleagues and students that might be have questions. And next, I'll give time for all of us to give a questions to Dr. Zamani. But first, we already have one questions from Ibu Hermania. She asked about the procedure, the impregnation of an ENCE. Maybe you can share the procedure, how it works.
Yeah, okay. Okay, for wet impregnation methods. Okay, this I think the simple or the the simple methods, wet impregnation methods compared to others method like Sojas and others. Okay, so this method we just dissolve metals nitrates in water. Okay, and then we put zeolite. Okay, in the we put the metal nitrate and dissolve with a small volume of water. Okay, small of water, and then we put zeolite sodium A. Okay, and then we stir the between zeolite and solution. Okay, and then we rest until 12 hours. Okay, for exhaustion, and then remove water. Okay, we put in oven. Okay, we put in oven at 100 degrees C for 12 hours. Okay, so we get a powder, and then we calcine at 55 degrees C using a furnace for 2 hours. Okay, that's a method for wet impregnation.
Okay, Ibu Hermania, hopefully what the explanation that Dr. Zamani just shared can answer your question. Next. Okay, so Dr. Zamani, she has further questions.
Yeah.
So from what you've explained, that means we don't have to do the steer until it I don't know, I forgot, mengendap. I forgot it. It's in English word.
Precipitated. Is it
precipitated? Yes.
Yeah.
Okay.
Okay. This one we need to stir. Yeah. When you mix metals and zeolite, we need to stir. Okay, and then stir around I think 1 hour. Okay, and then we rest the solution, and they have precipitate, means the solid akan mendak, precipitates. Okay, and then we put in oven to remove or we dry to remove water. Okay.
Okay, Dr. Zamani or Ibu Hermania
Yeah,
has another questions.
yeah.
Yeah, okay. Hopefully you can understand the questions. See right on the chat side, chat room.
That side. Where? Okay, chat. Okay, right. Selanjutnya kalau okay, you need to meet together because we use similar salt. Example here, we use nickel nitrates, and so you need to use Sevian nitrate, similar salt precursors. Okay, because when you use different like nitrates and chloride, okay, so they have some issue because chloride they has poisonous to catalyst. They can deactivated the surface areas. Okay, and also chloride we need use high temperature, more than I think 6 or 700 to remove chloride precursors. So I suggest we use nitrates because nitrate precursor we can remove at low temperature or medium temperatures around 4 to 500. We can remove nitrate. So we just get metals oxides. Okay. You can mix both the first and second together. The second one is after calcination and then impregnated with CE. Okay. I think you can try to do this methods or procedure. You need calcine nickels with zeolite first, and then you impregnate with CE. Okay, I think it's a good idea, but I don't know. Maybe it can give a better result.
Thank you very much, Dr. Zamani.
Yeah.
Here.
If any question.
Oh, you already. Okay. Yes. So Ibu Hermani already said that she understand what your explanation. So here we also have our students here. Maybe if our students can write in or cannot speak in English, you can also go to chat room and write your questions, and I will translate. And Dr. Zamani, I also believe that he can understand your questions. Yeah. Okay, another question maybe.
Kami, Ibu Sincha.
Yes, please, Professor Rainer.
Thank you, Dr. Zamani, for the wonderful research result that you present. The people that asked you before is our colleagues here in School of Chemistry. She is doing PhD in ITB, Indonesian, ITB Bandung. Yes. And she's struggling with the zeolite types of conversion process. So that's why she asked you many questions, and she's still asking more questions.
Okay,
But
you can maybe can email me if you have any
hopefully
further
you can.
question.
Yes. Dr. Zamani, it seems that your catalyst could be used for reducing organic compounds. Have you ever tried something, maybe not for carbon dioxide, but we can use your nickel, cerium, kaolin types of catalysts to do conversion of organic substances. Have you ever tried that before?
Not yet, Prof. Organic type like example sugar, it means sugar. So far not yet test organic compound.
Yes. Because we are struggling with doing stereoselective reducing of our molecules, because we need hydrogens to reduce the carbonyl groups in our compounds to making stereoselective types of alcohols. So that it could be your catalyst could be do the roles of doing an anti-selective reduction, maybe. I don't know. That's the idea of me.
Maybe can try.
Thank you, Dr. Zamani. I think Dr. Hermania still have another questions if you should check.
Okay.
Oh, okay. Yes, please. Ibu Hermania.
He's asking about the reactor.
Reactor.
Or maybe Ibu Hermania can go travel to Dr. Zamani's.
You can.
It's close by.
If you have any further question, you can contact me or email or message.
Because the catalyst that you showed, the SAM, is very is it crystal or
this SAM is
I mean the crystality.
The SAM, this one is SAM image for called zeolite sodium A. Okay, this I think is similar to commercial one. Okay, so like qubit image. Okay, so if we add another metals, okay, we add nickels and it means nickel and ceriums, so we can this metal we load in the surface of this one. So I have image for nickels and cerium, but I cannot show for in this sharing. Okay, so they have ceriums and nickels in the surface of zeolites.
Okay. That's right.
So this So this monthly research for postgraduate and staff or undergraduate?
Undergraduate.
Undergraduate.
Undergraduate, yes.
Okay.
We are on process of establishing the postgraduate.
Oh, okay, guys, good.
Yeah. And we ask you
Okay.
for help us for in the future, Dr.
Okay.
Zamani.
Can
Yeah.
can for
Actually, uh, we are trying to do double degree, and we are still on progress of discussing the issues between the UMPSA and Undana
Yeah,
in the next month, I think. Yeah.
yeah. Mobility, they have a mobility program so far.
Mobility. Yeah.
Yeah,
We haven't done that program yet, I think.
yeah.
Do you mean that? Yeah.
Means we send our student to Undana and then Undana send to us.
Exchange student. Exchange
Yeah,
program, you mean?
Yes, means exchange program, but
yes.
not to count the credit. I mean, just 1 to 2 weeks only, right?
Okay.
Actually,
Dr. Zamani,
Yeah.
it was
can I,
simple.
yeah, can I ask a question?
Yeah,
So
yeah.
from your slide, I can see that there is a difference between the XRD result A, B, and C. B and C seems it looks those two look similar, but it differs from A. So my
Yeah.
question is, what is the specific character that you are looking for in this research? Because you only have a two methodology characterization method only to make sure. So, just wondering, I'm wondering
Oh,
about the character that you're looking for. Is it enough to only to have two methodology to characterize your chemist?
okay. Okay. For SIDs, okay. So you can see here, A is raw materials, is kaolin. Okay, we convert kaolin to
Yeah.
zeolite sodium A and B. Okay, from A we convert to B, and then B we compare with commercial zeolite A. So we can assume that we successfully means success synthesize zeolite A. Okay, but this result not enough. We go to use send image. Okay, so send image also
Yeah.
we get a similar image if we compare to commercial one. Okay,
Mm-hmm.
also you can use FTIR. Okay, FTIR for other confirmation. Okay, I think
Mm-hmm.
two characterization for zeolite sodium enough, except
Okay.
if you have maybe you need to
The
more
mm,
details, so you need to go to more
yeah.
instrument or characterization.
Mm.
You see,
Okay.
Che?
So the further yes.
There
Yep.
is still
Yes,
one
Prof.
more question from Ibu Hermania. Was
Yeah.
the zeolite
Oh,
that you prepared still mesoporic structures, or maybe it changed, maybe?
Yeah. We get micropore for zeolite, but when we put put nickel and cerium, they change to mesopore.
Mm.
mm, Mm-hmm.
Okay.
Okay.
The chain to may support when we put nickel and surveillance.
Okay. Thank you, Dr. Zamani.
Yeah.
Yeah, maybe okay, Ibu Hermania still have questions.
Yeah.
Okay.
We have
Yes,
the
okay.
data, the details, because still in progress. We cannot to publish yet. After that, we can share the data. Okay.
Yeah.
As I said,
It's
Dr.
okay, Ibu
Zamani,
Hermania.
Okay.
Ibu Hermania is still struggling with the zeolite types of making catalyst.
Yeah. Okay, so we plan to scale up this catalyst and then apply to industrial pellet plant.
Dr. Zamani,
Yeah.
how did you end up with the cerium instead of using another metals?
Because I think the Syrian the best, as I said before, Syrian can they have oxygen vacancy, can enhance the CO2 absorption and also improve. See this one. This one, because Syrian they have oxygen storage capacities. Okay, and then they can store, facilitate CO2 activation and improve resistant carbon deposition. Maybe
Right.
we need to study about the stability after this. Is it this stable compared to nickels?
Right. Thank you.
Okay, right. Prof.
Okay. Yeah. Maybe we still have questions for our colleagues or students. We haven't got any questions from our students. Hopefully they can understand what Dr. Zamani has already shared. Yeah, but maybe can we got the material, the slides, the presentation slide?
Yeah.
Dr. Zamani?
Yeah, can. I can share this slide.
Okay, thank you.
Yeah.
Okay.
I will email Prof. When
Thank you, Dr. Zamani.
Yeah. Okay, it seems like we don't have any further questions from our colleagues and students. So thank you again, Dr. Zamani, that already shared with us your knowledge, your research finding. We learned so much this morning. So once again, thank you very much. We appreciate all your time and your knowledge that you already shared with us. Okay, so next, Prof. Rainer, maybe you can say something to Dr. Zamani as a closing statement for our
Thank
meeting
you,
today.
Ibu Sinche. Yes. Thank you, Ibu Sinche. Especially thank you, especially for Dr. Zamani, for sharing your research results. That is wonderful, insightful, and it's grateful for us. And on behalf of the Department of Chemistry, I would like to express our happy to have Dr. Zamani, and hopefully we can work further together with Dr. Zamani or Dr. Fashihi or colleagues from School of Industrial Science and Engineering in UMPSA. We we are seeking for doing further might be discussion about the double degree programs that we are running, establishing of the program, and we hope in the meantime we can discuss it with colleagues from the UMPSA, especially from the Faculty of Industrial Sciences and Engineering. And thank you for all of us as the participants. Hopefully, we can do MRT next month with Dr. Zamani's colleagues from another,
Yes.
another disciplines. Might be from organic or analytical chemistry, or might be from physical chemistry, and so on. Thank you, Dr. Zamani, and thank you for all of us. Hopefully, God bless us. Inshallah, we will meet again next month. Thank you very much. Thank you.
Yeah. Thank you very much, Professor Rainer. So to all of us that has that is in that are in this meeting, thank you for your time, and we will meet next month for another MRT. Again, Dr. Zamani, we will see you maybe. Okay. I'll close this meeting. Prof. Rainer, terima
Yes.
kasih untuk para
See you later.
Okay, thank you. Thank you, Prof.
teman. Ya.
Thank
Okay.
you.
Bye, Dr. Zamani.
Terima kasih
Okay,
berhormatnya.
Assalamualaikum.
Atau di